Swayam Prabha. Digital India. Educated India.
In the last class, we had looked at what is stress optic law, and we also saw what is the maximum stress information obtainable from a simple photoelastic experiment. We looked at that we need to find out fringe order n and theta at the point of interest. Then by invoking Moore's circle, it is possible for us to find out normal stress difference as well as in plane shear stress. Now, we will have to look at what is the kind of optical equipment that we need to use to find out the fringe order n and theta at a point of interest. And before we go into that, let us have a look at what we have learned in understanding polarization. So, here you have a natural light, then I put a polarizer, it allows only one component of light, and I want to investigate what is the status of polarization. I introduce another element which is physically the same and it is kept at different orientations to investigate. And when I do this, when I rotate this element, you find progressively the intensity diminishes, and when this axis becomes horizontal, that is perpendicular to the polarizing axis, whatever the light that comes out of the polarizer is completely cut off by the analyzer. So, what you saw was you saw only a black background, and another subtle point you need to note here is I am sending a white light. So, this phenomena is independent of wavelength. We have looked at a model behaves like a full wave plate. When it behaves like a full wave plate, it is a function of wavelength. When it behaves like a full wave plate, it is a function of wavelength. But on the other hand, when I have a plane polarized light which is impinging on the model, which comes out as plane polarized, and this can be cut off by analyzer which is kept at perpendicular to it. When the light vector is not a function of the phase retardation introduced, there is also a possibility to look at the wave in that fashion. Now, we will go and look at what happens when I keep a model loaded between the polarizer and analyzer, because the idea is we want to find out how the fringes get formed in a birefringent model that is loaded. So, what you find here? I have a polarizer, I have an analyzer, and I am sending a monochromatic light source, and I have a model which is birefringent, which is loaded. And what you find here? You have the background is still dark, and within the region of the model you find fringe contours, and you need to make a neat sketch of it. You first worry about light source, put the polarizer, put the model and put the analyzer. And what we find here is this is the simplest arrangement in which a plane polarized light is incident on the model. So, what you find here, when the ray hits the model, we label that axis as fast and slow axis, and we have no knowledge whether this is a fast or slow axis. This is only a representation, and I said this matters when I go to digital photoelasticity. for the kind of optical arrangements you have in conventional photoelasticity, whether it is fast or slow, it does not make much of a difference. Then what do you find here? One can use a monochromatic light source or white light for illumination. So, what I can do is, instead of monochrome light source, I can also put a white light source. So, what I find here is, when I put a white light, which is nothing but light source of multiple wavelengths, now I find one set of contours are colored, the other two contour that we saw, they still remain black. We will spend some time on looking at this again. We will go to monochrome. Now, what you have to understand, I have a polarizer and I analyze the light that comes out of the model only by using a simple analyzer, which is nothing but a polarizer, but its axis is kept differently. So, this will only detect whether the light that comes out of the model is plane polarized. If it is plane polarized in the same direction as the input light, then this will completely cut off the light, because that will be perpendicular to it, it will completely cut off. And when the model can allow plane polarized light as plane polarized light, we have looked at in the wave plate. If the wave plate behaves as a full wave plate, then whatever the light that impinges on the model, it goes out unaltered. So, a plane polarized light incident on the model will come out as plane polarized light, which is a function of wavelength. When the moment you say it, because it behaves like a wave plate, you will also have to bring in function of wavelength. That is the reason why we first look at only monochromatic light source impinging on the model. And you also have a very nice picture here. See, this shows that you have stress is continuous, that is the reason why you have a nice continuous contour. So, what I find here is, I could have the regions which are black are really those regions where the exit light from the model is plane polarized in the same direction as the input polarized light. Because the analyzer is kept horizontal perpendicular to the polarizer, that light is cut off. So, you see this as dark. And now, the question is, I see as two dark bands here, are they same as these other dark bands or not? So, what we will do is, we will now rotate the polarizer and analyzer combination, keeping them crossed, and let us see what happens. So, now I rotate them. So, when I rotate them, what I find is, one set of contours remain stationary, these contours keep changing and they sweep the entire model. And what you have here is, this dotted line show that you have the polarizer analyzer are rotated, they are kept crossed. What can you guess from this? What can you guess from this? When I was discussing about wave plates, I also mentioned, if the fast and slow axis coincide with the incident plane polarized light, what comes out of the model is simply the same as what is sent inside, there is no modification. And because it is aligning with the fast axis, it is not wavelength dependent. So, even when I say send a multi wavelength light, that will also be cut. We have to verify that statement, but you can conjecture this is what happens. So, what you can now appreciate is, when I keep a model in a plane polariscope, I see two sets of contours. One set of contours where the model behaves like a wave plate. Why I see multiple contours? The model cannot distinguish phase difference is 0, phase difference is 2 pi, phase difference is 4 pi, 6 pi, 8 pi, it cannot differentiate that. So, that is why I get multiple contours. So, one possibility of fringe formation is the model behaves like a wave plate. So, the input plane polarized light comes out as plane polarized light unaltered. The second possibility is when I rotate the polarizer analyzer crossed, at different points you have principal stress direction. When it coincides with the principal stress direction at the point of interest, whatever the light that is sent, that is also cut off. I will also provide further explanation, then it will become clear. First make the look at the animation and find out how they are. Now, what we will do is we will change the wavelength, we will change from monochromatic light source to polychromatic light source. So, now I go for a polychromatic light source, and as I said, these are colored. This I have not provided the reason, but this I have already provided. When I rotate the polarizer analyzer, you have this as a black contour. It is independent of wavelength, because those contours come because your polarizer analyzer coincides with the principal stress direction at the point of interest. So, whatever the wavelength of light you send, it comes out as plane polarized, because the model need not behave like a wave plate. The polarization change is not because of model behave like a wave plate, it is because the input polarized light passes through the fast axis, there is no component perpendicular to it. So, whatever the wavelength you send, whatever the light that you send, it is cut off by the analyzer, because it is perpendicular to the polarizer. So, what you have here is in a plane polariscope, it is very clear now, one observes two contours, namely isochromatics, which show contours of difference in principal stress, and isoclinics, they are nothing but contours of principal stress direction. And what happens here when I want to analyze what are isochromatics? In a white light source, I see them as richly colored. So, what happens is, when I keep the polarizer, when I keep the analyzer crossed, when the model behaves like a wave plate, full wave plate, the input polarized light comes out as polarized light, which is a function of wavelength. So, what you see when I send a white light is, out of the several colors of white light, one color is cut off, because it will behave differently at different points depending on the stresses developed. It may be a full wave plate for red wavelength, it may be a full wave plate for blue wavelength, for different values of stress. So, one of the colors is cut off. So, you see the rest of the colors, that is why in a polychromatic light source, you see the isochromatics as colored. So, you see white minus extension of one of the colors, and isochromatics, the model behaves like a full wave plate. When model behaves like a full wave plate, wavelength of the light also is to be looked at. When the wavelength changes, it will not behave like a full wave plate. What behaved like a full wave plate for red wavelength will allow some retardation, more than 2 pi or less than 2 pi, it will not be exactly 2 pi. So, what you find here is, in a plane polariscope, you find beautifully two sets of contours, And now we will also go and develop a logical explanation. Suppose I want to develop the intensity equation, you can anticipate that it should be a function of difference in principal stress as well as function of theta. So, you will anticipate if I develop the intensity equation, it should be a function of delta as well as theta, all that we will look at. Now, we will again develop this argument in the subsequent slides, we will see systematically. Why do fringes get formed? We will try to provide a logical explanation. We have already seen the logical explanation, and this is another verification of whatever we have discussed. To simplify our effort, we will have the light source to be a monochromatic one. And what I do is, I have a model which is loaded, which is kept in the field of view. And what do you anticipate? Because the model is loaded, the state of polarization of the incident light changes from point to point depending on the principal stress direction and the magnitude of principal stress difference. Because when you take a disk and then load it, near the load application point you will have very high stresses, regions away from it, it will be stressed low, and because it is a stress is a continuum, what you have is you have an elastic continuum. So, when you apply the load, the variations are smooth, that is why you see beautifully smooth fringe contours. Stresses vary gradually from point to point, and you also see smooth fringe contours. And what we do is, by keeping an analyzer, we find out when the light is cut. We find out when the light is cut. The analyzer will cut the light when the plane of polarization is perpendicular to it. For the plane of polarization to be perpendicular to it, the input polarized light should come out unaltered. And in a plane polariscope, in conventional photoelasticity, we always keep polarizer analyzer crossed. If you go to digital photoelasticity, people also tried keeping them parallel, keeping them at arbitrary orientation, but in conventional photoelasticity, polarizer and analyzer are always crossed. So, what I have here is, the first possibility is light extinction happens when the principal stress difference sigma 1 minus sigma 2 is such as to cause a relative phase difference of 2 m pi, where m is 0, 1, 2, etc. And this I have taken from a different optical arrangement, which is called a circular polariscope, for clarity. So, I see one set of fringe contours, and when I send a monochromatic beam of light, I see this as black and white contours, whereas we have defined isochromatics as iso means constant and chroma means color. Colored isochromatics are seen only when the illuminated source is a white light. So, suppose I change the source of light as white, I see them as colored contours. So, you get a fairly good idea that this is how isochromatic contours appear in the case of a disk under diametral compression. Because stress is varying gradually from point to point and you are having an elastic continuum, I see this as beautiful contours. And the regions where you have shades of light that is coming in, where the retardation is not 2 m pi, it will be either less or more than this. So, it will allow some amount of retardation. You will have an elliptically polarized light, all of that light will not be cut by the analyzer, some light will come and hit the screen. And we have also seen why a fringe appears as a band. only is those points where sigma 1 minus sigma 2 is 2 m pi, exactly you will have this as plane polarized coming out, and this is cut off completely by the analyzer, which is kept perpendicular to it. In other cases, state of polarization will be different. You will also have a component along the horizontal direction, that is why you see fringe as a band. There will be some small amount of light which your eye is not sensitive to distinguish. And what is the other possibility? We have seen one possibility, we have to look at other possibility. For clarity, what is done is, I have shown one representative isoclinic, and what you need to understand here is, I can have multiple branches. I can have one isoclinic here, another isoclinic here. I may also have in some situations a small curve here. So, what is important here is, when the polarizer axis coincides with one of the principal stress directions at the point of interest. And what is tried to be shown here is, I have the reference axis shown in brown, and these are the principal stresses at the point of interest. Their magnitude may be different, but if you look at the orientation is same. And here again only isoclinics are shown for clarity, and in fact, there is no unique optical arrangement which would provide only isoclinics. You have an optical arrangement which will filter out isoclinics and show isochromatics, which is possible. We will also see in a circular polariscope, and I have always been mentioning, in most of the experimental techniques, it is desirable to get fringe information separately. In some cases you cannot separate them out, in some cases you can separate them out. In a circular polariscope, I can filter out isoclinics, I can see only isochromatics, but in a plane polariscope I will always see isochromatics and isoclinics together. For clarity of understanding, isoclinics are shown here, but there is no optical arrangement that is available to get you this. What you could possibly do is take a photoelastic material which has a very high value of f sigma. So, for the given load applied, you may not have significant formation of isochromatics. That is the only way which you can see only isoclinics with some level of clarity. And you have a picture of the actual fringe pattern seen in a plane polariscope, and this is the isoclinic, and this is the axis at the point of interest, and the orientation of these axes remain constant. And I have again emphasized, when the polarizer axis coincides with one of the principal stress directions, light extinction is not wavelength dependent, because I do not have another component, I have only one component passes through. So, whatever the light that comes out of the model is completely cut off, and these are known as isoclinics, meaning contours of constant inclination, and it will take some time for you to appreciate what these contours are. I think the picture is reasonably clear. Do you want me to enlarge it? I can also replay. So, what I have initially, I have this as only isoclinics drawn, and you find this is the reference axis, and this is the orientation of principal stresses at the point of interest. The length of the vector indirectly indicates its magnitude. What is attempted to be shown here is sigma 1, sigma 2 can have different values, the orientation remains constant. And if I see what happens in a plane polariscope with white light as illumination, I see the isochromatics superposed with isoclinic, and this is what you see as isoclinic. And we can also have another way of looking at it. We will also have a look at what way we can represent. What I do is I rotate the polarizer analyzer crossed combination in steps of 10 degrees. One can record isoclinics in steps of 10 degrees and plot them. And what you have here is, what is shown here is, I have an isoclinic here which is labeled as 10 degree isoclinic, and what you find here is sigma 1 and sigma 2 can have different magnitudes, but their orientation remain constant in this isoclinic. And if I go to a 20 degree isoclinic, the angle becomes 20 degrees, and this you have to extract data by several different positions of the polarizer analyzer combination. You do not see this information available in one experimental exposure. This is what you have in conventional photoelasticity. That is why people said, can I plot the isoclinic field for every point in the model domain, and digital photoelasticity has now achieved. You may have to take a few images and process the intensity, and it is possible for you to generate plots of this nature by post processing the data acquired. In a conventional polariscope, I have to keep it at 0 degrees, 10 degrees, 20 degrees, 30 degrees, and for each of them go and carefully draw the isoclinic sketch. And there is also something very interesting. I will not give you the answer. See, this is a circular disk for which you are given the stress field equation, and you can find out what is the principal stress direction at every point of interest. And there is something very interesting, this isoclinic meets at the point in the boundary. It will meet only at a specific point, and this will also enhance your understanding of solid mechanics. Go back and look at what point it can meet, go back, and because this is a free surface, this is a free surface, and this isoclinic has to come and cut at only at one particular point, which you can look at from solid mechanics. That will give a very interesting result. Take that as a home exercise. So, what you have as isoclinic is little subtle, and for me to get plots of this nature, I need to conduct a series of experiments, and from that you record them carefully in a conventional photoelastic analysis. And we will look at what are isochromatics. We have looked at what are isoclinics, we will look at what are isochromatics. These are the isochromatics, and what you have here is the direction may be different, but the difference of sigma 1 minus sigma 2 will remain same on a isochromatic contour. So, that is the only difference. Direction will not remain same here, direction will keep changing from point to point, but the difference of sigma 1 minus sigma 2 will remain same. And this you can actually put it in one of your earlier contours, you do not have to redraw this, you have one of the isochromatics, on that you can put this information. So, what you find here is on an isoclinic contour, principal stress direction is a constant, on an isochromatic contour, the magnitude of sigma 1 minus sigma 2 remains a constant, but the individual values of sigma 1 and sigma 2 and their orientation theta can vary. So, we have exhaustively looked at from a qualitative argument what are isochromatics and isoclinics. And now, what we have to do is we have to go and look at, can we establish mathematically that whatever we have looked at from a logical explanation and find out what is the equation of intensity of light. For that we need to go and develop the mathematics, and the simplest way to do is doing a trigonometric resolution. And what we will do is, let the linearly polarized light coming out of the polarizer in general is k e power I omega t, because I can have a cos omega t and sin omega t terms. For the purpose of this discussion, we will consider only the real part. When we go to Jones calculus, we will retain as k e power I omega t. And let us look at how we can label the axis when the light passes through the model, and we will also have a larger picture of it. So, what I have is, I have a light source, and the first optical element I have is polarizer, which is labeled as E1. Then what happens? You have the model which is shown with enlargement here, that I have this is the point where light enters the model, and this is the point where light exits the model. For clarity, these are shown distance apart, and at the incident plane I will have two axes. We will label them as E2 and E3. They are essentially slow and fast axes at the entry point, and these axes will remain because I am looking at a two dimensional model. Essentially it is a plane. For convenience, we have some finite thickness. For clarity, this is shown as enlarged. So, you will have two axes E4 and E5. Then I represent the analyzer, which is kept horizontal. The polarizing axis of analyzer is horizontal, and I put this axis as E6. So, what I need to do is, I need to write the light vector for E1, find out how do I write the light vector at E2 and E3. Then I have to find out how to write E4 and E5. Then finally, I will have to look at only the component E6 that is filtered by the analyzer. So, if I do all that, I will know what is the exit light that is coming out, which I could simplify and then find out what is the intensity of light transmitted, and we have already anticipated that it should be a function of delta and theta. If we get that, then all our qualitative argument fits nicely with the mathematical development. And because it is a very simple optical arrangement, trigonometric resolution is very comfortable and simple, and it also provide you a level of understanding which you will not get otherwise. So, we will go by a trigonometric resolution. Later, we will also analyze the same problem by using Jones calculus, and you will find Jones calculus is very comfortable when I have several optical elements in the optical bench. Here I have only a polarizer, model and analyzer, it is very simple. So, trigonometric resolution is quite all right, and we will see how do we do the trigonometric resolution. And what we will do, we will simply say E1 as cos omega t, k cos omega t. So, I have an amplitude, I have this as cos omega t, and you have to recall when we discussed retardation plates, this is the input polarized light that hits the model. As soon as it hits the model, you have the amplitude split along directions E3 and E2. So, you can write what is E2 and also what is E3, it is fairly simple. You make your own attempt, then I will show you the what you have is when it hits the model, model is loaded. So, for one incident light you will have 2 refracted beams. Because of this orientation, this is 90 minus theta here. So, I will have a component will pass through E2 and another component will pass through E3. Essentially the amplitude will change. So, I have this as k sin theta cos omega t and E3 as k cos theta cos omega t. It is fairly simple. If you recall the discussion that we had on retardation plates, we spent sufficient time on looking at what happens to the incident light when it hits the model and what happens within the thickness of the retardation plate. A similar thing we will have to look at here. So, for directions E2 and E3, you are able to write the light vector comfortably. And how do you write for E5 and E4, E4 and E5? This is the these are the axes at the exit of the model. So, within the model the light has acquired a relative retardation. Suppose I say retardation is delta, I can say no retardation along direction 4 and full retardation is in direction 5. I can also put 0 and delta. I can also put delta by 2, minus delta by 2 and plus delta by 2. This is for our convenience. Keeping in view that I am going to develop Jones calculus, where the matrices will look nicely, we will take the choice of minus pi by 2, minus delta by 2 in the slow axis and plus delta by 2 in the fast axis. That is just for convenience, mathematics is not going to change. So, that is what we will do now. So, what we say is the model introduces a phase difference delta and let E2 be the slow axis and E3 be the fast axis of the model. And E2, E3 are if it is slow and fast, E4 is slow and E5 is fast, and we want to do it for E4, which is considered as a slow axis. So, what I will do is the same amplitude of that will not change, but the phase I subtract minus delta by 2 and on E5 I add plus delta by 2. So, what I have here is E4 turns out to be k sin theta cos omega t minus delta by 2 and E5 is k cos theta cos omega t plus delta by 2. So, do you understand the way that we go about in writing the changes in the light vector as it passes through different elements of the polariscope? We start after polarizer. When it hits the model, we look at, when it hits the model, we do not look at it as one plane, we look at hits the model at the front surface, leaves the model at the other surface. Theoretically, when you are looking at a plane model, it is as thin as a plane, but physically we use a finite thickness. So, we bring in some engineering approximation, and we also say that the principal stress direction remain constant within that thickness, and we do this as two operation. First, there is a intensity amplitude, the amplitude of the light vector changes. The second case, we put appropriately the retardation, then it comes out. So, when it comes out of the model, this E6 what it will do? This is nothing but your analyzer. This will allow only component of light that is parallel to this. If for any other component, if it is perpendicular to the, if the light vector is perpendicular, it will completely cut off. So, we want to write an expression for what is the light transmitted by E6. That is very simple. I have E4, you know this angle, I can find out what is the contribution from E4 and what is the contribution from E5. Can you write it? Can you write what is E6? So, what we do here is, because the optical arrangement is very simple, we are in a position to do trigonometric resolution, and stage by stage we are able to incorporate what changes that happens to the incident light vector. And we know E6 will pass only the light component parallel to this. We write an expression for E6 in terms of E4 and E5. That is fairly simple, E4 cos theta minus E5 sin theta, and which is also simplified. If you go back, I said for all this you need to have knowledge of trigonometric identities. It is a very simple step, it is not difficult at all. So, you take this component E4 multiply by cos theta, multiply this by sin theta and do a simplification. This is the component of light that is transmitted by the analyzer, that turns out to be k sin 2 theta sin delta by 2 into sin omega t. So, what we have anticipated? We have anticipated that this should be a function of delta, which is related to sigma 1 minus sigma 2 and theta. So, I have k sin 2 theta sin delta by 2, both are appearing. But what do you record? I do not record the complete light characteristic. All the sensing elements are sensitive only to the intensity, not the complete light vector. Okay. So, that we will have a look at it, what happens. Human eye is also a light sensing instrument. Human eye and all other light sensing instruments respond to the intensity of light. It is a very key concept. Why we always look at intensity of light is because we respond only to this, and there is a relationship. The intensity is proportional to the square of the amplitude. The intensity is proportional to the square of the amplitude, and this is a point to clarify. You have rapid time variations which cannot be detected, and for a sodium light we have the frequency as 5.1 into 10 power 14 hertz. So, you do not perceive the time dependent component, and you are sensitive only to the intensity of light transmitted, and intensity of light transmitted is square of the amplitude. So, what we will have to look at is, we have got the E6, we will look at this E6 expression and we will square the amplitude and find out what that expression gives. So, that will give you beautifully an explanation what we see as fringes in a plane polariscope, and I am not going to do the complete derivation. I am going to give you the final result, which you can have a look at it, and you can actually go back and do this as your homework. And I label this as IP, the P denotes it is a plane polariscope, and I get the final expression as IA sin square 2 theta sin square delta by 2. So, we have, with very simple mathematics, we have been able to find out what is the intensity of light transmitted in a plane polariscope when a model is kept loaded. And we have said this intensity is proportional to square of the amplitude. Whatever we have put as I A, it accounts for the proportionality constant and the amplitude of incident radiation. So, now we have to investigate when does this intensity expression goes to 0. So, it can happen for two cases. I can have a situation where sin square delta by 2 goes to 0. So, those contours correspond to sigma 1 minus sigma 2, they are called as isochromatics. You can have another possibility where theta goes to 0. When theta goes to 0 essentially means the polarizer axis coincides with the principal stress direction at the point of interest. When it coincides, you have only one light beam travels through the thickness of the model, that is completely cut off, and this is independent of wavelength. When the incident light coincides with the polarizing axis at the point of interest, which is nothing but the principal stress direction, it gets cut off and it is independent of the wavelength. The light getting cut off is independent of the wavelength. So, that is why you see two contours and the isoclinics appear black even in white light. The difference is when I rotate the polarizer analyzer combination, these black contours also move. And there could be questions like, suppose you are given a plane polariscope, how will you identify whether it is an isochromatic or isoclinic? What are the ways that you can think of? I have said one which you can easily derive. You keep the polarizer analyzer combined and rotate it. When I rotate it, one contour will move with it, that is isoclinic. Can I make the other contour to move? Why do you say no? You have to say what is that I have to do. Suppose I change the load, what will happen? When I change the load, does the principal stress direction change? Then you have to go back and brush up solid mechanics. See, in linear elasticity, when I increase the load, stress magnitudes change, principal stress direction do not change. So, that is why I always say, when you learn experimental stress analysis, your fundamentals of solid mechanics become clearer and clearer, because certain things you assume, you think you know, when you are confronted with a question, you do not know what the answer. So, I can also make the other contour move. If I change the load, the contours that are functions of the load are isochromatics, the contours that are not functions of the load are isoclinics, because isoclinic will not change, should not change. In linear elasticity, they will not change. So, that is the way you distinguish between an isochromatic and isoclinic, even in a plane polariscope with simple monochromatic light source. If you are given a white light source, you have a luxury. I see colored contours and then I have black and white contour, but there is one caution. I do not know, this is not very prominently seen in a circular disc. The 0th fringe order is always black. So, you have to distinguish even in a white light source what is 0th fringe order and what is isoclinic. I have to make a distinction, and though in general fringes move, when I apply the load, what will happen to the 0th fringe order? Think about it. See, for every rule there will be an exception, there will be a rule and there will be exception. You should understand both, you should know the rule as well as the exception and why it is so. So, this is what you will have to understand. So, in this class we have started looking at what is the optical arrangement that we need to conduct a photoelastic experiment, and we said that a simple incident of plane polarized light is good enough, and I get two contours. One contour corresponds to sigma 1 minus sigma 2 for which I have to find out the fringe order. Right now we have not discussed how to find out n, that we will keep it as a separate discussion. First time we have seen fringes and we have classified one set of fringes as isochromatics and another set of fringes as isoclinics. How to find out n, how to find out theta, we will have separate discussion. Now what we will do is we will go and develop our mathematical skills better, because we want to go for a circular polariscope where I will have more than one optical element in the path of light, and for me to analyze trigonometric resolution is not convenient. I need to develop a special type of calculus called Jones calculus, that we will take it up in the next class.